Hi. So I recently got another washing machine motor. So you remember this old motor I had? I was using my previous videos. If you don't watch them, well, it's my new washing machine motor. The old one didn't get destroyed, and that's a relief. And it's my new motor. And I thought it would be a good idea if I can dream up the experiments I can come up with these two motors and do them in my video. So let's get going. Now for this washing machine motor, the wiring is not the same as the old motor. So this is how it's wired. So these 6 terminals go like this. The top two are the tachometer to measure the speed of the motor and send the voltage to control circuit of the washing machine. These two, the two after the tachometer connections are of the field winding, and the very bottom two are of the armature winding. So to wind it as a series motor, we get this, and we connect one here and the other one here, as you are seeing. It connects the field and armature together. We get another two wires, the positive and the negative, and connect them like so. Input, positive, and output. And these two are going to be connected to our supply. So now, for my first experiment, I've thought of coming up with this idea. Running this as a motor on a self-excited washing machine motor. See how fast it turns. So if you remember this motor, in my previous videos, in my very first video, I used it as a self-excited generator. And I didn't have any other washing machine motor, until now. And I'm going to connect this one to that and see how fast this one turns. So let's wire it up. Okay, so this is the setup, it's wired up. So this generator here is wired as a series motor, and it self-excites when the rotor spins at high enough RPM. And the wire is connected as a series motor. And the output of this series motor is connected to that series motor, as you are seeing. Now I'm wearing my glove for safety purposes with the rope. I turn the rope, and the motor should spin, if that gets self-excited. So let's do that. So now, as you can see, the motor is going to be behaving like the motor. You're not supposed to see the generator, because I'm going to turn to the rope. Now, supposedly, this should turn when the generator self-excites. And you should see this turn. I have some tape with it so you can see it turning easily. And so apparently it didn't work. Probably I turned it too slowly because I lost control of the rope. And 1, 3, 2, 1. Didn't turn. Let's try it again on the reverse, except this will be the generator and the other one will be the motor. Let's do it. So there's the other motor, and the generator is in front of you, and now you should see that turn when the generator turns. So 3, 2, 1. And so it worked. It turned. Let's do it again for the fun of it. Probably I turned the other generator in reverse. It's probably why it didn't work. But anyway, let's do it again. 3, 2, 1. So what on earth is happening here? So what you're seeing here was the generator, and that's what was turning was the motor. Now, how is the generator powered, you ask? Again, there are no hidden batteries in this generator. It is not free energy, and it is not connected to the mains. This is self-excited, which means there is visual magnetism in the generator, and the armature converts that into electric, and the rotating conductor in the generator, i.e. the armature, converts that into electrical energy. And that electrical energy is sent to the field winding, which generates a stronger magnetic field, which generates more electricity in the armature, and it self-excites, and there is electricity in the circuit, and behaves like a generator. And the electricity makes this motor turn. So now, let's do another experiment. So this is for the other experiment. So, On YouTube, some people connect a battery to the field winding of a washing machine motor, connect an external mechanical energy source, and the output of the armature winding is high voltage DC, usually use light up bulbs. I'm doing the same thing here, except instead of a battery, there is a self-excited generator powering the field winding, so we can see how much voltage we get. So this multimeter is going to measure the voltage and the short circuit current of this generator here. So this is how it should work. This circuit should work like this. That over there is the self-excited generator. It self-excites and generates electricity. And that electricity goes to the field winding of that motor. And when that motor is turned, there should be a high voltage out of the armature winding, which this meter should read. So let's do that. And before you ask, this meter is supposed to measure DC because the generator here generates DC. The meter can measure both DC and AC, but the generator generates DC because it's a commutator. If there was springs, I would have probably been able to run an AC motor or two. But anyway, on with the experiment. Ideally, for a generator, I use a combustion engine. But they're extremely dangerous, so I can't have any. At least for now. So I've got to stick with ropes. On the motors. So now, anyway, watch the voltage display on the meter screen as the generators are turned. And... such an idiot, I forgot to turn on the meter screen. I'm such an idiot. Anyway, let's try again. Again, so retake. Watch the voltage on the meter screen as the generators are turned. Don't look at the generator, look at the meter screen. And... as you saw, there was a voltage. So let's do it again. So this is a retake. And now in this retake, because I said we're going to do it again, we're measuring the voltage. After this, should be measuring short circuit current of the electric generator. That are on this setup. And 3, 2, 1. As you saw, a voltage generated. Now let's measure the short circuit current of the electric generator. As you see, it's set to amps DC. So right now it's 0 amps. When I turn it to my hand, there's about 1 milliamp. 14 milliamps. So let's do it. Let's wind the ropes and let's let it go. So now, watch the meter as it reads short circuit current. As you saw, a current was generated. So now in this setup, it works like this. This is the electric motor. The generator here is powered by some 9-volt batteries. The field one is powered by 9-volt batteries, and after one is left to run this. And we will see how fast this will turn when the generator sends a high RPM and when the field winding is excited. So let's do it. This sort of generator is known as a separately excited generator because the field winding is excited separately, unlike series and shunt generators. The field winding is controlled on separate circuits. The armature and field winding are electrically separated. So now, these two connections are the connections to the field winding of the generator, and we connect our power supply to them, an 18-volt battery. So I have another plan. I got this from a broken toy car, and I'm going to connect the batteries in the battery terminals, and on other side there are contacts. I'm going to connect the field winding of the generator to those. There should be a spark, and from the inductor making of the, because the winding is an inductor, and the field winding should be excited after that until I disconnect it, as you are now seeing, should be seeing. So the batteries are connected. Down there, you have the field winding, and I connect it. As you're seeing, there's a huge arc. Which indicates excitation, that it's excited. So now, I turn it. Now, feast your eyes on the motor and not on the spark. And... uh-oh. Must be lose connection. Okay, so now I'm going to connect it, the field winding connected, and this is what turned. Apparently there is connection in the armature winding. So in this circuit, this is the load, and the generator had some windings inside it. The field winding uses a magnetic field in the motor, and the armature converts the magnetic energy into electrical energy when it is turned. The magnetic field gets the, the armature converts mechanical energy into electrical energy when there's a magnetic field. When a magnetic field is present. And electrical energy being sent to the motor. So now, when it is not excited, there should be much less electricity and the motor should not turn, as you are seeing. When I connect it, I saw it turn. That was because I connected the batteries. But as you saw, when I didn't connect the batteries, the motor did not turn. The motor did not turn. And it will work if I do it on the other way around. Now, if I connect a 9-volt battery, see what happens. So, now, I'm going to connect the 9-volt battery. So this is what you should see spinning when the generator is excited. So, as you can see, I'm going to link the 18-volt battery pack to the field winding. As you can see, when it's excited, there's an arc from the spiking, very high voltage generated. Anyway, forget the arc. So, connected. I'm going to turn the generator, unless the battery turns good, the motor should turn. And so the motor turns, but not as much as with the 4.8-volt batteries. But that was because 4.8-volt batteries were capable of delivering currents much higher than 9-volt batteries. But not just for fun, let's do it again. Connected, and as you saw, it turned. Perfect. Okay, so for the next experiment, this is how the circuit's going to behave. That's the battery pack. This is the first generator. The power from the battery goes into the field winding, and the running goes generate electricity. The power from the armature winding goes into the field winding of this one, and the armature output of this one goes into the meter, which you shall read the voltage of. And the meter reads the voltage output of this generator, which should supposedly be higher than the output of this, because this generates a higher voltage than this one, because this feeds this. So let's do it. And we're going to try to measure the short circuit current of this thing. So I'm trying to measure DC voltage. Right now it's at 0. When you turn this on without excitation, it should go at 20 millivolts. Now, when I excite both of them, first I have to excite the first one, the batteries. Because notice not both of them are separately excited. There is no self-excitation. So I see the spark? Probably can't. But whatever, it's excited now. So now watch the display on the meter screen. And oops. Yes. Okay. Note to self: never be an idiot. Only pull the motor before you pull the thread. So let's try again. And the 1, and the 2, and the 3, and oh sorry, forgot to connect the batteries. Starting, and the 1, and the 2, and watch the meter screen. As you saw, a voltage was generated. Now let's measure short circuit current. So as you can see, we're setting it to to measure a current of maximum 10 amps. Connected to 10 amps. Now it's supposed to measure short circuit current. Focus on the batteries. And now a current should be generated that's about 7 milliamps when these two are turned when there's excitation. So let's do that. Okay, so this is supposed to measure DC currents of up to 10 amps. Everything is wired. Connect the batteries. Hold the thread. And the 1. And the 2. And as you saw, a current was generated. Okay, so I come up with another ridiculous idea. What the voltage 1 can generate, not 2. 1 universal motor can generate. Let's find out. Okay, so now the meter is hooked up to measure voltage of one single generator. The other one's not involved in the circuit. Of one single generator, I want it excited. And as you saw, it generates about 50 volts. That's pretty high. That's really a short circuit current. Now, of course, when under short circuit, the generator is going to be extremely hard to turn, and I may either hurt my fingers, or probably destroy something. So, there's another way. I don't load the generator, or I don't feed excitation, and I want to turn it at high speed. I suddenly connect the load or excitation. That's a pretty bad idea when it comes to the load. Because you connect the load, when I short circuit the generator while it's turning at high speed, it can cause an explosion. And yes, it won't end well. So there's only one option left. To leave the load there on the circuit at all times and connect the excitation circuits to excite the field. So that's what I just said. And a 1, and the 2, and the... I just saw a current was generated. Now, because I don't give a damn, I'm going to run it while it's excited and shorted. And excited. High current. Good. So I thought of another stupid idea for an experiment. I thought of connecting this drill battery to the electric motor, but I realized it was too dangerous. Here are some of the highlights. Or, I forgot about this, I can also modify the winding and connect it to a UPS, because the winding is modified, it will draw less current and produce an even stronger magnetic field. And if I also modify the armature, that thicker windings and fewer turns, I can make that one, and as a instead of a commutator, I can generate a very high voltage at a very high current, AC, not DC, and I can run my AC motor in peace. Yay. But, alas, I can't modify it, as I can't open up the motor, as I will destroy the armature. So I'll have to stick with what we have. Let's connect to the mains. Let's connect the field winding to the mains and turn the armature winding, even though it's a very stupid idea. So, let's do it. I have got to remember to never, ever, ever connect loads to power supplies with improper connectors, as doing so can pose a very dangerous electrical hazard. So I've got to come up with an alternative to connect the power supply to the field winding of the motor, the generator. So I have option number 1 out of 3 options. Option number 1 is to find a safe connector to connect the drill batteries to the field winding safely. Yeah, right. I don't have that other equipment. Never mind. Proceeding to option number 2. Connect a battery pack. A different battery pack that can be connected to the field winding safely. I have a battery pack. Alas, I do not have a soldering iron to solder the connection to the battery pack. So forget that. Option number 3. I can either connect a high voltage capacitor bank to the field winding. That sounds tempting. Or I can connect the mains to the field winding. Option number 3 sounds like the only safe option. even though it includes the highest, it needs the highest voltages. So here's my setup for this idea. We have the plug, which goes to the channel connector, and the channel connector connects the field winding of the motor. And the armature winding should generate an incredibly high voltage, because the field winding generates an incredibly strong magnetic field, which can generate an incredibly high voltage and current in the rotating conductor, which is the armature. But alas, it's a very dangerous and useless idea. Useless. Why? It's useless because the voltage is too high to power anything useful. If I connect this to the mains and turn the shaft at high speed, assuming the fuse never blew and the windings never melted, the voltage and current will be too high to power anything. If I connect it to something, a mains appliance, it should explode immediately, or stop, or melt, or stop working, or it should not work. And it's another reason why it's stupid and dangerous. This idea is stupid and dangerous because of the fuse. If I connect this to the mains, the field winding will draw an incredibly high current alone. In a series motor, the field winding has an incredibly low resistance to electric current because it is connected in series with armature winding. In a series motor, the field winding has an incredibly low resistance, a resistance as low as possible, and a number of turns as low as possible because it is connected in series with armature winding, which also needs electric currents to run. And if, on its own, the field winding draws an incredibly high current, and that is with no armature winding to limit the current. And that current is well over 13 amps, which is the rating for the fuse, so it should blow. Then which is why it would act extremely quickly in the circuit. We turn the shaft at high speed, and while it's losing speed slowly, the mains electricity is supplied to the winding. An incredibly high voltage should be generated in the armature for a very short period of time until the fuse burns out. But, alas, the voltage is too hard to be measured on multimeter. And no, this is not inductive spiking. The high voltage is not generated via inductive spiking. It is generated via the generator principle. The moving conductor, which is the armature, generating electricity from the magnetic field generated by the field winding. Though connecting the drill battery would be tempting, because I generated up to 122 volts DC with the generator on the drill battery, and up to 1 amp on low speed. Imagine at high speed. It will probably generate more than enough to power a house. Alas, I can't, because it has a commutator. If it had slip rings, then maybe. But we've got to go into modifying the motor, and I don't know how to do that, so I've got to stick to DC for now. But this is good enough for our projects, so now all I have to do is connect this to the mains and it should work. So let's do that. But the capacitor bank sounds tempting. Okay, so this piece of junk no longer works, and I can't plug it into the mains. This plug no longer works. Stupid plug. So I have to come up with another idea to generate a high voltage on the armature winding. So I come up with a ridiculous idea of generating electricity with some batteries, but that wasn't going to cut it because the voltage on the batteries is too low to generate a high enough voltage on the output. The drill battery is incredibly dangerous, so it can't generate a very high voltage. No. So I come up with another puny idea, using this DC motor as an electric generator. It's capable of generating some pretty high voltage under high speed. This can generate some 40 volts when it is used as a generator and the shaft turns at an incredibly high speed from an external mechanical energy source. But it is under load. The field winding is a heavy load for this motor generator, so the speed will be reduced dramatically. So first, this is how it's going to work. This has to be turned at high speed, and while this shaft turns at high speed, I turn this motor to excite the field winding, and this motor speed should reduce dramatically as a very high voltage is produced, which is read by this multimeter over here. So let's do that. Okay, so this multimeter is going to read the voltage output of the electric generator. It's reading DC volts, as you are seeing. For now it is 0, because nothing's turning. Now, First, I'm going to turn the washing machine motor at high speed with no field winding excitation. The voltage on the field winding should be incredibly low, if there even is any. So now watch the multimeter screen. And as you can see, there is half a volt, or maximum 0.7 volts. Now, and that was with no excitation. Now, watch the multimeter screen once I turn the electric the small DC generator which powers field winding at a low speed. The voltage on the multimeter should be low, but much higher than before. So watch the multimeter screen. At low speeds, when I turn the small electric motor to excite the field winding, I get about 4 volts, which is pretty good. Now I'm going to turn both at very high speed. The speed of the motor should decrease dramatically, so watch the multimeter screen. Okay, so everything is all set up. Let's run the generator and pray we get a high voltage DC. I wish it was AC, so I can run my AC motor for a change. Apparently there was a much higher voltage than this, but it was for such a short time that the meter can't read it. Let's try again. Note to self: get a high speed, get a method get a method of generating high speed for a long time, because the meter won't read it if it's for a short time. Anyway, let's do it. So I wind the threads on both motors. The generator which powers the field winding and the generator which powers the multimeter, and we're gonna let it rip. 3, 2, 1. 55 volts. You saw that there was 55 volts generated on the multimeter screen. The voltage could have been much higher, and I think it was, because there was a high voltage spike, which was so short that the meter couldn't have read it. If those two were running at high speeds for a long enough time, the meter would have read a much higher voltage. But as you can see, this method can generate a high voltage. And it's not a complete failure. That's a relief. Yay! Yay! Not. Okay, yay. It generated some high voltage. No, it's DC. I can't use that to power my television. Should have come up with a better plan to do that. So I'm left with two options. One, get an inverter. They cost money. And this can generate a stable voltage on its own. And it's special circuitry to stabilize the voltage. Or the inverter will probably get fried. Option number 2, get slip rings. Okay, sounds like a reasonable idea. So I can build a motor of my own and add slip rings. And connect a power supply that generates constant 12 volts, like that drill battery for a change. And I can get safe connectors and not be an idiot with it next time. Okay, that sounds like a genius idea. But I don't have safe connectors for the drill battery. So I've got to come up with another idea. But hey, at least now I'm going to take the other washing machine motor and make it spin at an incredibly high speed before the string snaps, that is. So I should again come up with another way to turn the motor at a high speed without hurting myself. A combustion engine sounds like a good idea. Or even better, I can get a bicycle and turn the shafts. Only problem being, I don't have a belt. So I'll come up with a better idea next time.